In this lesson, we will learn how to evaluate the impact of a mitigation strategy on a specific risk within our simulation model. We'll use an incremental or marginal approach, comparing three scenarios. First scenario, without mitigation. Second scenario, without the risk itself. Third scenario, with an active mitigation strategy. So our starting point is the baseline scenario. We begin with a probabilistic scenario that includes uncertainties and risks without applying any mitigation strategy whatsoever. We ensure that all risks are activated. We run 5,000 iterations and we analyze the result at the 70th percentile. The results without mitigation, the project finish date is August 20th, 2026, and the total cost is approximately $31,000. This serves as a reference scenario or baseline. Now we run a second scenario without the main risk. We had previously identified the risk number 7, technical and integration issues, as the most relevant. We deactivate this risk in the risk sheet and run the simulation again. The results, excluding the risk, the new finish date is August 9th, 2026, and the new total cost is approximately $29,000 at the 70th percentile. So there's a net savings of 11 days and $2,000. This is a hypothetical scenario where the main risk does not exist. The third scenario is applying a mitigation strategy. We now simulate the active mitigation of risk number 7. In the risks sheet, the segment from columns U to AD allows us to control how we implement each component of a mitigation strategy. In cell U9, we enter a value of 1 to activate the mitigation strategy for this risk. We activate duration mitigation on V9 and cost mitigation on W9 with values of 1. We estimate the following effects. Frequency reduction enters 75% in cell X9. Duration reduction, also enter a 75% in cell Y9. Cost impact reduction, also enter 75% in cell Z9. The probability of success, 90%, entered in cell AA9. A Bernoulli, a binary function, simulates this probability. In 90% of the iterations, the mitigation is successful. In the remaining 10% of the iterations, the strategy incurs a cost, but has no effect on the reduction of duration or cost. The estimated implementation cost model as a distribution, a minimum cost of $200 on cell AB9, a most likely cost of $300 on cell AC9, and a maximum cost of $500 on cell AD9. We run the simulation again with the active mitigation plan. The results at the 70th percentile, a finish date of August 9th, 2026. A total cost of approximately $29,600. A net improvement in cost due to mitigation, approximately $1,400. A net time savings due to mitigation, 11 days. Now, simulating this mitigated scenario yields the following probabilities. On time and under budget, a probability of 55%. On time but over budget, 13% probability. Late but under budget, 15% probability. And late and over budget, 17% probability. So we conclude, this exercise shows that 1. Mitigating a risk can reduce both time and cost. 2. The incremental analysis helps us to understand the net effect of the risk. 3. The probabilistic model helps evaluate whether it's worth investing in the mitigation strategy. In the next lesson, we will explore how to compare multiple mitigation strategies to choose the most efficient.